Welcome back. In this video, you will learn how to take the derivative and the integral of a power series. Let's get to it. Alright, so previously we have seen that power series represent functions that are only defined for a domain of x values for which the series converges. And so since a power series represents a function, naturally we might be interested in determining the derivative or the integral of that function. And so let's start by taking a look at the derivative of a power series. Remember that a function f of x is equal to a power series where we have the sum from n equals 0 to infinity of a sub n times x minus c to the power of n. All right, and this is a power series centered at the value of c. And so here I have the first couple terms of this power series. We have a sub 0, then a sub 1 times x minus c to the first power, then we have a sub 2 times x minus c squared, and then a sub 3 times x minus c cubed, and so on. Right, and so these terms of this power series create a function f of x. And so if we want to find the derivative f prime of x of a power series, what we can do is take the derivative of each of these terms individually. And it's important to note that for each of these terms, that a sub 0, a sub 1, a sub 2, and a sub 3 are all constant values, right? If we're taking this derivative with respect to x, then all of these values that are dependent on n are just going to be constants. The only part of these terms that we are going to treat as a variable is x. All right, so keeping that in mind, let's take the derivative of each of these four terms that we have written out for this general form of a power series. So first off, we have a sub 0. The derivative of a sub 0 is just going to be 0 because that is a constant, and the derivative of a constant is 0. All right, now for our second term, it gets a little bit trickier. Now we have a sub 1 times x minus c. So what we have here is a constant times a quantity where we have x, a variable, minus another constant. And so for example, if we were to replace a sub 1 and c with actual constants, let's say it's something like 3 times x minus 2, how would you take the derivative of an expression like this? Well, the constant multiple is going to remain the same, right? So the derivative of this expression would be 3 times the derivative of x minus 2. And the derivative of x is just 1, and the derivative of negative 2 is 0. So we would be multiplying 3 times 1, which would be equal to 3. And so in this case, we have a sub 1 as our constant times x minus c. The derivative of this term will be a sub 1 times 1 minus 0. And so the derivative is just going to be a sub 1, the value of that constant. All right, and then if we look at our next term, now we want to take the derivative of a sub 2 times x minus c quantity squared. And to do that, we are now going to need to use the chain rule. And so if we go back to our little example here, instead of having x minus 2 to the first power, what if we had x minus 2 squared? Now how would we take the derivative of an expression like this? Well, we would still have 3 on the outside, but then for this quantity here, we would need to use the chain rule. We would start out by taking the derivative of the outside function, which is the quantity squared, and then we would multiply by the derivative of the inside function. And so the derivative of the outside function would involve multiplying the exponent down and then subtracting 1 from that exponent. That would be the power rule for derivatives. So we would have 2 times x minus 2 to the first power, and then we would multiply by the derivative of the inside function. And the derivative of x minus 2 is just 1, so we're multiplying by 1, which doesn't really change anything. So if we were to apply that same strategy to this general form of that term, we're going to have this power multiplied down by a sub 2. So we're going to have plus 2 times a sub 2 times the quantity x minus c to the first power times 1. But we don't need to write that first power, and multiplying by 1 doesn't change anything. And so this is the derivative of that term. And then if we were to take the derivative of the next term, it would be a very similar process. We would add 3 multiplied down, subtract 1 from that exponent, and that will be your derivative. because from the chain rule, the derivative of the inside function is just 1, so we don't really need to worry about multiplying by that derivative. We will just have 3 times a sub 3 times x minus c squared, and our terms would continue on from there. All right, and so now we have taken the derivative of each of these terms from the general form of a power series, and now what we can do with these terms is express them as their own power series. All right, so if we take a look at our terms here, and by the way, we don't need this plus 0, that doesn't affect the rest of our terms. What we can do here is look for a pattern in these terms and use that pattern to form a power series. All right, and so what we're going to have is a sum from n equals 1 to infinity. Now I say n equals 1 because that first term where n was equal to 0 was just equal to 0, so that term really isn't a part of this derivative. This derivative starts with a first term of a sub 1, so we're going to start at n equals 1. And what's happening with each of these terms is the value of a sub n is being multiplied by the value of n, and then we're being multiplied by this quantity of x minus c to the power of n minus 1. Right, so I'm going to write that out, and then I'll explain why this is true. We're going to have n times a sub n times x minus c to the power of n minus 1. Right, so when n equals 1, we have 1 times a sub 1 times x minus c to the power of 1 minus 1. So this power would be 0, so we have x minus c to the power of 0, which is 1, and so we would have 1 times a sub 1 times 1, which is just a sub 1. Then when n equals 2, we'll have 2 times a sub 2, which is what we have right here, times x minus c to the power of 2 minus 1, which is a power of 1, and so we just have x minus c to the first power, which is what we have right here. And so this pattern will continue on for the rest of these terms, and it should be obvious why that is true, because if you compare the form of this derivative to the original, it's just the power rule for derivatives in action. We multiply this exponent of n down, so we have n times a sub n right here, and then we subtract 1 from that exponent to have n minus 1. All right, so that's really all that we're doing here to take the derivative of a power series. We multiply that exponent down and subtract 1 from that exponent, and now we have f prime of x. All right, and so the derivative of a power series can be represented by this series right here. So the sum from n equals 1 to infinity of n times a sub n times the quantity x minus c to the power of n minus 1 will be f prime of x. All right, so that's the derivative of a power series, but what about the integral of a power series? Well, we can take a similar approach to what we did for taking a derivative of a power series. We can start out by integrating each term for the general form of a power series, and then coming up with a way to represent those terms as a power series. And so if we integrate f of x dx, we'll start by integrating a sub 0. Now, a sub 0 is just a constant, and when you integrate a constant, you multiply it by the variable you are integrating with respect to. So the integral of a sub 0 would be a sub 0 times x, but since our power series is centered at c, instead of just multiplying by x, we're going to have a sub 0 times x minus c. All right, so just x minus c to the first power. And then for our second term, we want to integrate a sub 1 times x minus c. And so if we were to look at a specific case scenario like we did with the derivatives, let's say that a sub 1 is 3 again, and c is 2. So we have 3 times x minus 2, and we want to integrate that with respect to x. What we could do to integrate this is use u substitution. We could set u equal to x minus 2, and the derivative du dx will be equal to 1, since the derivative of x is 1 and the derivative of negative 2 would be 0. And what that means is that du is equal to dx, and so this would be equal to the integral of 3 times u du. And then what we could do here is use the power rule of integration, and we would find that this is equal to 3 times u, but we're going to add 1 to the exponent of u. So 1 plus 1 is 2, and then we're going to divide by that new exponent of 2. And then, of course, you would add c to the end of that integral. All right, and then, of course, we would replace u with what we set it equal to, which is x minus 2. But now notice, because the derivative of u was just equal to 1, there were no extra constants tagged along with du, and so the integral was pretty easy to find. In fact, all we have to do for all of the terms of this power series is just use the power rule for integration on x minus c as if it was just x, right? And so what I mean by that is if we look at the integral of a sub 1 times x minus c, we would have a sub 1 times x minus c increase the power of x minus c by 1, so we'll have a power of 2, and then we will divide by that new power. That is the power rule of integration. And if we do that again for our next term, a sub 2 times x minus c squared, we would have a sub 2 times x minus c to the power of 3, we're adding 1 to that exponent, and then divide by that new exponent again. All right, we are allowed to continually do that because the derivative of x minus c is just going to be 1. We can entirely skip that use substitution step and just use the power rule of integration for each of those terms. All right, so we could do that one more time and have a sub 3 times x minus c to the 4th power divided by 4, and we could continue on from there. All right, we're just adding 1 to that exponent and then dividing by that new exponent. Okay, but then remember, we are taking an integral of a function, and so we have to remember to add plus c to that integral, right? And so I kind of ran out of space here at the end, so instead of writing plus c over here, I'm actually going to write it at the beginning. So if I rewrite this a little bit, we'll have that the integral of f of x is equal to that constant c plus a sub 0 times x minus c. Okay, so don't forget that constant of c that you always need to add to an integral. All right, and so those are the terms of the integral of a power series, but how can we actually represent these terms as another power series? Well, we can go through a very similar process of what we did for the derivative of a power series. We can simply just use the power rule of integration on our general form of a power series, and the result of that will represent all of these terms that would be in the integral of a power series, right? And so what we'll have is that the integral of f of x dx is equal to that constant c plus the sum from n equals 0 to infinity of a sub n times x minus c to the power of n plus 1, right? We add 1 to our exponent for x minus c, so we have the quantity x minus c to the power of n plus 1 right here. And then we need to divide by that new exponent. So we will divide by n plus 1. All right, and so this power series right here represents every single one of these terms that would result from integrating each term of the original power series, right? And so if we were just to check a couple of them, when n equals 0, we want to have this term right here, a sub 0 times x minus c to the first power. If we look at what happens when n equals 0, we'll have a sub 0 times x minus c to the power of 0 plus 1. That would just be the first power. So we would have x minus c to the first power, just like we have right here. And in the denominator, we would have 0 plus 1. And so we're just dividing everything by 1, which doesn't change anything. And so this represents the first term when n equals 0. And then let's check n equals 1 as well. When n equals 1, we'll have a sub 1, just like we have right here. And then x minus c to the power of 1 plus 1, which would be 2. So we'd have x minus c squared, just like we have right here. And then we will divide by 1 plus 1, which is 2. And that's what we have right here. Okay, so you can see that this power series is the integral of the original power series. It represents every single one of these terms given a certain value of n. All right, so all we have to do to integrate a power series is add 1 to the power for the quantity that includes x, and then divide by that new exponent. Okay, and so this is the power series that represents the integral of a power series. All right, and so now that you have seen how to take the derivative of a power series, as well as how to find the integral of a power series, we can now talk about the radius and interval of convergence for the derivative and integral of a power series. In fact, it's not all that different from just finding the radius of convergence and interval of convergence for a regular power series, because the derivative and integral are actually going to share the same radius and interval, except the endpoints might be different. The integral or derivative may gain or lose one endpoint or two endpoints compared to the original power series. And so what we're going to do next is look at a power series, find its derivative, find its integral, and then determine the interval of convergence for the original function, the derivative, and the integral. and I want you to see the differences between the intervals of convergence for those three different functions. Okay, and so let's take a look at that next. All right, so here's the power series we're going to work with. We have that f of x, our function, is equal to the sum from n equals 1 to infinity of x to the power of n divided by n. And we want to find the derivative and integral of this power series and then determine the radius and interval of convergence for those three different functions. All right, and so let's start by just finding the derivative and the integral of this power series. So I'm going to start with the derivative. F prime of x is going to be equal to the sum from n equals 1 to infinity of the derivative of x to the power of n. And so if we multiply that exponent down, we will have n times x, and then we need to subtract 1 from that exponent, so our exponent will be n minus 1. And that will still be divided by that denominator of n from before. All right, so any part of your series that involves n and is not the power of x, you're going to leave alone. Nothing is going to happen to that n in the denominator because we're taking a derivative with respect to x. And so the only n that's going to change is that power of n for x. Okay? So this is our derivative, but note that there is some cancellation that's going to occur here. We have an n in the numerator and denominator, and so our derivative is just the sum from n equals 1 to infinity of x to the power of n minus 1. So I'm going to rewrite this. We're just going to have x to the power of n minus 1. This is our derivative of this power series. All right, and so now let's take a look at the integral of f of x dx. That's going to be equal to the sum from n equals 1 to infinity of the integral of x to the power of n. So we're going to add 1 to that exponent. So we'll have x to the power of n plus 1, and then we're going to divide by that new exponent of n plus 1. So we're going to have n plus 1 in the denominator, but don't forget about that other n that is also in the denominator. We need to keep that n as well. All right, and so this is going to be the integral of our power series. X to the power of n plus 1 divided by n times n plus 1. All right, but don't forget that when you take the integral of a function, you need to remember to add that constant c, right? We would want to add plus c to that power series, but that's not going to be too important going forward when determining the radius and interval of convergence, because that plus c isn't actually part of the sequence whose terms we are summing together, right? That plus c would be moved to the front of the power series, so it doesn't really have an effect on the radius or interval of convergence. So while it's important to include that when you're just finding the integral of your power series, I'm just going to erase it here to keep things simple going forward. Okay, so finding the derivative and the integral of your power series is not too difficult. It just involves using the power rule for derivatives and the power rule for integration on the part of your power series that involves x. All right, so it's really not as complicated as it might originally seem. But now what we want to do is find the radius and interval of convergence for each of these three functions, right? We now have the original function, f of x, we have the first derivative, f prime of x, and we have the integral of f of x as well. Now I've already told you that the radius of convergence is going to be the same for all three functions, but I'm going to go through the process of finding the radius for each function just this one time so that you can see that that is true. But in general, you only need to find the radius of convergence for the original function, and that radius will be the radius for the derivative and the integral as well. And so let's get started. Let's use the ratio test for our original series and find the values of x that make this series a convergent series. And that will help us find the radius and interval of convergence. All right, so we're going to use the ratio test. So we'll have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, so we will have the limit as n approaches infinity of the absolute value of x to the power of n plus 1 divided by n plus 1. That right there is a sub n plus 1, right? We just replaced each of these n's with n plus 1. And now I'm going to multiply by the reciprocal of a sub n, and that will be the same as dividing by a sub n, okay? So in this case, a sub n is x to the power of n divided by n, but I'm going to flip the numerator and denominator and that will be the same as dividing by that fraction. All right, so we're going to have n divided by x to the power of n. Okay, and by the way, if you're not familiar with what I'm doing right here for the ratio test, be sure to watch my video on the ratio test as well as my first video on power series. Both of those are going to be very helpful in understanding the work that we are going to go through right here. Okay, but now at this point, what we want to do is simplify this limit. First thing I notice is that we have x to the power of n plus 1. We can split up that power and just have x to the power of n times x to the first power. Okay, and so this is equal to the limit as n approaches infinity of the absolute value of x to the power of n times x to the power of 1, or x to the first power. That would just be x, and then that's multiplied by n divided by n plus 1 times x to the power of n. All right, now at this point, notice that we have x to the power of n in the numerator and denominator, and so those are going to cancel out, and now what we're left with is the limit as n approaches infinity of the absolute value of x times n divided by n plus 1. All right, now the next thing I like to do is separate n from x, right? What we can do is just put the absolute value bars around x and move n divided by n plus 1 to the outside of those absolute value bars because the values of n are always going to be positive. All right, so what we're going to have is that this is equal to the limit as n approaches infinity of n divided by n plus 1 times the absolute value of x. So that's the same thing we have over here. It's just rewritten a little bit differently so that the absolute value bars are only around x. And now we can focus on evaluating the limit as n approaches infinity of n divided by n plus 1. Okay, now if you're very familiar with evaluating limits at infinity, you'll recognize that this is a fairly simple limit to evaluate. We have the limit as n approaches infinity of a rational expression where the numerator and denominator are algebraic, and so we can look at the highest powers of n in the numerator and denominator to help us decide what the value of this limit will be. In this case, the highest power of n in the numerator and denominator is 1, right? We have n to the first power in the numerator and n to the first power in the denominator, and so since those highest powers are equal, the value of this limit as n approaches infinity will be equal to the ratio of the coefficients for those two terms. So in this case, it will be 1, the coefficient of this n, divided by 1, the coefficient of this n. So this limit is just equal to 1 divided by 1, which is just equal to 1, and so we have 1 times the absolute value of x, which is just equal to the absolute value of x. All right, and so the absolute value of x is the result of our limit for the ratio test, but the ratio test says that our series only converges when the value of this limit is less than 1. So we need to set the absolute value of x to be less than 1. And now at this point right here, we can determine the radius of convergence for our power series. We have the absolute value of x, which is the variable part of our power series, and we're saying that it's less than 1, and so 1 is the radius of convergence. All right, so I'm going to say r is equal to 1. So that's the radius of convergence, and that is going to be the same for the derivative and the integral as well. But I will still show you the work so that you can see that this is true. But for now, let's work on finding that interval of convergence for f of x, or at least we'll almost get there, and I'll explain that in a little bit. Remember that the absolute value of x being less than 1 is the same as saying x is less than 1, but it's greater than negative 1. All right, this is the same as the absolute value of x less than 1. And so what we have right here is our interval of convergence for this power series, but we haven't checked the endpoints yet, right? We just know that our series is convergent from -1 to +1, but it's not including those two values. We don't know. We're going to have to check each of those endpoints individually to determine if we should have a closed bracket around either of those endpoints. All right, the ratio test only allows us to determine what two endpoints the values of x for which our series is convergent for lie between, not if those two values are included. Okay, so we'll look at that in a little bit. Remember that the original power series has a radius of 1, and it's convergent for values of x between -1 and +1. And now what I want to show you is that we're going to find this same result for both the derivative and the integral. And once I show you that that is true, then we will go about checking the endpoints, -1 and 1, to see if they should be included for the interval of convergence for each of the three series or each of the three functions. that is where the difference will be, okay? But before we get there, like I said, let's check and make sure that we get the same radius and interval of convergence without checking the endpoints for the derivative and the integral. And so let's start with the derivative. Okay, so we're going to use the ratio test again. We're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, this time for the first derivative. And so in this case, we'll have the limit as n approaches infinity of the absolute value of x to the power of n plus 1 minus 1, right? Because a sub n is x to the power of n minus 1. So if we replace n with n plus 1, we have n plus 1 minus 1. Okay, and that will be divided by a sub n, which is x to the power of n minus 1. All right, now x to the power of n plus 1 minus 1 will reduce to just being x to the power of n, right? Positive 1 and negative 1 will cancel out. And so this is equal to the limit as n approaches infinity of the absolute value of x to the power of n divided by x to the power of n minus 1, but we can split up that exponent, and we would have x to the power of n times x to the power of negative 1. All right, and now you can see that we have x to the power of n in the numerator and denominator, and so those are going to cancel out, which is just going to leave us with the limit as n approaches infinity of the absolute value of 1 divided by x to the power of negative 1. But now if we move x to the numerator, that will make that exponent positive 1. And so what we really have is the limit as n approaches infinity of the absolute value of x to the first power. And the limit as n approaches infinity of the absolute value of x is just going to be the absolute value of x because there's no n's in this expression, right? We have the absolute value of x, not n. And so if we're looking with respect to n for this limit, this absolute value of x is technically just a constant. And so we would say that this limit is equal to the absolute value of x. All right, and then once again, this limit for the ratio test needs to have a value less than 1 in order for that series to converge. And so we would set this absolute value of x less than 1, which means that the radius is equal to 1. And so we have the same radius of convergence for the derivative as the original function. And then we could rewrite the absolute value of x less than 1 to be negative 1 less than x less than positive 1. All right, and so that interval of convergence is negative 1 to 1. But we haven't checked the endpoints yet, and so those parentheses could change to brackets, but once again, we will get to that later. We still need to check that the integral also has the same radius and interval of convergence, ignoring the endpoints. And so, now that you've seen that the derivative shares the same radius as the original, let's finally take a look at the integral, and then once we have checked that, we will check the endpoints to see if they should be included for each function. Okay, so let's take a look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, but this time for the integral. And so we'll have the limit as n approaches infinity of the absolute value of a sub n plus 1, which if we look at our integral here, each of these n's is going to increase by a value of 1. So we're going to have x to the power of n plus 2, right? If this n is n plus 1 plus 1 plus 1 will be n plus 2, and that will be divided by n plus 1 times n plus 2, right? This n becomes n plus 1, and this n plus 1 becomes n plus 2, okay? And then we're going to multiply this by the reciprocal of a sub n, which is the same as dividing by that fraction. All right, that's the quick little shortcut that I take when I'm working with an expression that is rational for the power series. Rather than writing out a complex fraction of one fraction divided by another, I just take the one from the numerator and multiply it by the reciprocal of the denominator. All right, so we're going to take this expression right here, a sub n, and flip the numerator and denominator, and then we'll have the reciprocal, which is what we want to multiply by a sub n plus 1. All right, so we'll have n times n plus 1 divided by x to the power of n plus 1. Okay, so now right away, I see that we have a quantity of n plus 1 in the numerator and denominator, and so those are going to cancel out. And then before we rewrite our limit, I also see that we can split up these powers for x. We can have x to the power of n times x squared, and x to the power of n times x to the first power. So we'll have that this is equal to the limit as n approaches infinity of the absolute value of x to the power of n times x squared times n divided by n plus 2 times x to the power of n times x to the first power. All right, and now we have x to the power of n in the numerator and denominator, and so those are going to cancel out, and we will just be left with the limit as n approaches infinity of the absolute value of x squared times n divided by n plus 2 times x. Okay, now at this point, I want to separate x from n, right? Because these absolute value bars only affect x at this point. I'm not worried about the absolute value of n or n plus 2 because that's always going to be positive since our values of n are from 1 to infinity. All right, so this will be equal to the limit as n approaches infinity of n divided by n plus 2 times the absolute value of x squared divided by x. Okay, so I just separated the n's from the x's right here. But now x squared divided by x is just x, right? So we can just rewrite this to be the absolute value of x, okay? And now we have the limit as n approaches infinity of n divided by n plus 2, which is a rational expression with a numerator and denominator that are algebraic, and they both have n raised to the first power, that is the highest power of n, and so the limit as n approaches infinity of this expression will be equal to the ratio of the coefficients for those two terms. So this limit will be equal to 1, which is the coefficient of this n, divided by 1, which is the coefficient of this n. So this limit is equal to 1 divided by 1, which is 1, and so this is equal to 1 times the absolute value of x, which is just the absolute value of x. All right, and so once again, we have found that the absolute value of x is the result of the limit for the ratio test. It's the exact same result that we got for our derivative and the original function. And so we're going to set that less than 1, because when the value of this limit is less than 1, this power series will converge, or this function will be defined for those values of x. And so once again, we have found that the radius is equal to 1, and that our interval of convergence, without checking for the endpoints, will be the values of x greater than -1, but less than +1. All right? And so now you have seen that for a power series, its derivative and its integral all share the same value for the radius of convergence and have the same interval of convergence other than whether the endpoints are included or not. Okay, so for all future problems where you need to find the interval of convergence for a power series, its derivative, and its integral, you only need to go through the ratio test one time. You can use it for your original function, find that radius of convergence, and this interval where you haven't checked the endpoints yet, and then just check the endpoints for the function, for the derivative, and for the integral. And that is what we are going to do now. All right, and so let's start with the original function, or the original power series. Let's start by checking -1. Let's check that endpoint first. When x is equal to -1, our power series will be the sum from n equals 1 to infinity of -1 to the power of n divided by n, right? We just replaced x with -1 since that's what we're setting it equal to. And now, does this series converge or diverge? If it converges, that endpoint will be included, but if it diverges, then that endpoint will remain not included. We will keep this parenthesis rather than making it a bracket. All right, well, if you recognize this series, this is actually the alternating harmonic series because we have -1 to the power of n divided by n. The regular harmonic series is just 1 divided by n, but this is the alternating harmonic series, and this is a convergent series. All right, but if you didn't know that, you could use the alternating series test. And remember that the alternating series test says that a series is convergent if it meets two requirements. The first requirement, you look at the limit as n approaches infinity of the sequence from your series, but you remove the part that makes it alternating. So instead of having -1 to the power of n divided by n, you would just have 1 divided by n. So that would be our sequence for our limit. And this limit needs to be equal to 0. And in this case it is. The limit as n approaches infinity of 1 divided by n is 0. So that's equal to 0, which checks out. And then the second requirement is that that sequence needs to be decreasing. So a sub n plus 1 needs to be less than or equal to a sub n. The next term of the sequence needs to be less than or equal to the previous term. And so comparing a sub n plus 1 to a sub n, we would have 1 divided by n plus 1 and 1 divided by n. And 1 divided by n plus 1 will always be less than or equal to 1 divided by n because this denominator is always going to be bigger than this denominator. When a fraction has a larger denominator, the value of that fraction is smaller. And so that second requirement is met, which means that from the alternating series test, this series converges. All right, so if you didn't know that this was the alternating harmonic series, the alternating series test also tells you that this series converges. Okay, so since it converges, we have just shown that for x equals -1, this original power series, or this function for this power series, is defined for that value. So instead of having an open bracket around -1, it will be closed. So we will now include -1 in that interval of convergence for the original power series. Okay, so now we've checked x equals -1, but now let's check x equals +1. And so when x equals +1, our series will look like this. We'll have the sum from n equals 1 to infinity of 1 to the power of n divided by n. But 1 to the power of n, as long as n is finite, which it would be in this case, is just going to be equal to 1. And so we really just have 1 divided by n as the sequence for our series. And this series right here is the harmonic series, not the alternating harmonic series, but the actual harmonic series, which is a p series where p equals 1, which means that the series diverges. All right, and so when x equals 1, this power series diverges, and so the endpoint of 1 remains not included for the interval of convergence. And so -1 to 1, including -1, is the radius of convergence for the original power series. Okay, but now let's take a look at the derivative for each of those endpoints. If we take a look at when x equals -1 for this series, our derivative, we will have the sum from n equals 1 to infinity of -1 to the power of n minus 1. Right, we just replaced this x with a -1, and so now we have the sum from n equals 1 to infinity of -1 to the power of n minus 1, which is a divergent series, right? If you were to use the alternating series test on this series, that first requirement would not be met. If you looked at the limit as n approaches infinity of the sequence from our series, not including the part that makes it alternating, right, this -1 to the power of n minus 1 makes it alternating, the sequence would just be 1 because all we have here is -1 to the power of n minus 1. And so the sequence is 1, and the limit as n approaches infinity of 1 is just equal to 1, and that's not equal to 0, which means that the first requirement is not met, which means that this series diverges via the alternating series test, or you could also say via the divergence test, since that's essentially what we just checked here. But either way, when you have a series of just -1 to the power of n minus 1, or n plus 1, that series is divergent. Okay, and so since this diverges, -1 will remain not included in the interval of convergence for the derivative. And so you can already see that this is going to be different than the interval of convergence for the original function. -1 was included in this interval of convergence, but it will not be included for the derivative. All right, and now let's check when x equals +1. We will have the sum from n equals 1 to infinity of 1 to the power of n minus 1. And 1 to the power of anything that's finite is just 1. So we just have the series for the value of 1. And so this series would just be 1 plus 1 plus 1 plus 1 plus 1, which just gets bigger forever, right? This series is never going to converge to one value. And you could check that with the divergence test. If you just take the limit as n approaches infinity of this sequence, you would have the limit as n approaches infinity of 1 is equal to 1, which is not equal to 0, which means that this series diverges. All right, so what we have shown is that for both endpoints, our series diverges, which means that both of those endpoints will not be included in the interval of convergence. And so the interval of convergence for the derivative will be -1 to 1, not including either of those endpoints. And so now we have confirmed the interval of convergence for the derivative. And now we have one function left, or one power series left, and that is the integral of our power series. And so, if we take a look at the endpoints one more time, but for the integral, let's start with x equals -1. we will have the sum from n equals 1 to infinity of negative 1 to the power of n plus 1 divided by n times n plus 1. All right, we just replaced this x with negative 1. And now we have an alternating series that we can test to see whether it converges or diverges. And so if we use the alternating series test, let's check the first requirement. Let's take the limit as n approaches infinity of our sequence, but remove the part that makes it alternating. So we're just going to have 1 divided by n times n plus 1. Or if you wanted to, you could rewrite this denominator to be n times n, which is n squared, plus n times 1, which is n. So this denominator could just be n squared plus n. All right, and so as n approaches infinity, this denominator is going to increasingly get larger. We're going to have 1, a fixed value, divided by an increasing denominator, or divided by infinity. You could view it like that, and that is always equal to 0. So this limit is equal to 0, so the first requirement for the alternating series test is met. And then let's check the second requirement. We need to make sure that this sequence is decreasing, that a sub n plus 1 is less than or equal to a sub n. So we'll have 1 divided by n plus 1 squared plus n plus 1 compared to 1 divided by n squared plus n. All right, we just replaced each of these n's with n plus 1 for the a sub n plus 1 term. Now comparing these two values, this denominator is always going to be bigger than this denominator because we're squaring a value that is 1 larger than this value, and then we're adding n plus 1 rather than just adding n. And so this denominator will always be bigger, which means that this fraction will always be smaller in value than this fraction. And so our sequence is decreasing because a sub n plus 1 is less than or equal to a sub n. All right, so that checks out, which means that from the alternating series test, that our series converges. Okay, so since this series converges, when x equals negative 1, that value, or that endpoint, will be included in the interval of convergence. And so I'll erase that open bracket, and we will replace it with a closed bracket. Okay, and so now we have one more endpoint to check. We just have to see what happens when x equals positive 1 for this series. So if we back it up here, let's take a look at when x equals positive 1. And so if we do, we will have the sum from n equals 1 to infinity of 1 to the power of n plus 1 divided by n times n plus 1. All right, now 1 to the power of n plus 1 is just going to be 1. 1 raised to any power is 1, as long as that power is finite. And so this would be equal to the sum from n equals 1 to infinity of 1 divided by this denominator, which we can rewrite to be n squared plus n if we were to multiply n through this quantity. So we have 1 divided by n squared plus n. Now, if we use a divergence test on this series, the limit as n approaches infinity of 1 divided by n squared plus n is 0. So the divergence test doesn't tell us anything about this series. And so we need to use another test to determine if this series is a convergent series. And in this case, what I'm going to do is use a comparison test. This series is really close to being a p-series, right? We have 1 divided by n raised to a power of 2 plus n. And so what I'm going to do is compare this to a p-series using the limit comparison test. So I'm going to make a note of that. There's the limit comparison test, and we're going to compare it to the sum from n equals 1 to infinity of 1 divided by n squared. This is a p-series where p is equal to 2, right? We have 1 divided by n to the power of 2, and so since that power is 2, the value of p is 2. All right, so this is a p-series where p is equal to 2, which is greater than 1, which means that the p-series converges. And so, from the limit comparison test, we need to take the limit as n approaches infinity of the sequence from our original series divided by the sequence from our comparison series. So we'll take the limit of 1 divided by n squared plus n divided by 1 divided by n squared. But of course, that would be the same as multiplying by the reciprocal of 1 divided by n squared. So instead of writing it like that, we will have 1 divided by n squared plus n times n squared divided by 1. All right, that will be the same as dividing by 1 divided by n squared. Okay, so if we simplify, this is equal to the limit as n approaches infinity of n squared divided by n squared plus n. Now this limit for the limit comparison test, as long as it is equal to a finite value, meaning it's not infinity or negative infinity, we can conclude that this series shares the same convergence as our comparison series. Okay, so if we take a look at this limit, I see that we have a rational expression, and the numerator and denominator are both algebraic. They both have powers of n that we can compare, and the highest power of n in the numerator is 2, and the highest power of n in the denominator is 2. And so since those powers are equal, this limit, as n approaches infinity, will be equal to the ratio of the coefficients for those two terms. So we'll have 1, which is the coefficient of n squared, divided by 1, which is the coefficient of n squared down here. So this limit is equal to 1 divided by 1, which is equal to 1, which is a finite result, which means that from the limit comparison test, we can conclude that this series converges just like the comparison series. All right, so since this series converges, we now know that when x equals 1, this power series, the integral of our original series, will include positive 1 in its interval of convergence. And so I will remove that open bracket and make it closed. And now we have the interval of convergence for all three of our power series: the original, the derivative, and the integral. And if you noticed, all three of them are different. That might not always be the case. You could have two that are the same, but it is important to realize that they very well could be different, like they are here. The radius will always be the same, but the actual interval of convergence for these three power series will most likely be different. Okay, and so with that, you have now seen how to take the derivative and the integral of a power series and how to find the radius and interval of convergence for a derivative and integral of a power series. Okay, and so with that, this is all I had for this lesson, but if you want to see some more examples of finding the derivative and integral of a power series, as well as finding the radius and interval of convergence for those series, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. Okay, and if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, and so I will see you next time.